All right, this lecture is going to be kind of more the end-all be-all kind of thing. This is end number 22. I really want to wrap things up into just this nice bow and circle relationships, every single thing that I can get out of them. Things that we've looked at before, using inscribed angles, central angles, and such, tangent lines, and we're going to explore more into secants, things called secants, which work with tangents, and chords, and lengths and angles and everything like that. So this one, I'll also work on classwork number 8 with you on this one as well as we keep moving on. You'll see classwork number 8 right here. I want to do these problems with you. Just make sure that it all makes sense. Like I said, wrap it into a nice, pretty little bow. The most difficult part of this unit, again, is regarding so many rules and so many different things you have to recognize for yourself. Like I said, even for me, sometimes I have to take a step back, look at a problem for a while. It takes some time. So we'll go with stuff that we have just been talking about. First of all, with intersecting tangents and what conclusions we can draw from this. And I'll go one by one here. Let's start with this angle X and what it represents in terms of B and A. I'll start with it by talking about lines here. And so what I'm going to do is, for these conclusions, I'm going to first draw out a rule, and then we'll draw a conclusion based on that. And then for the examples, for the practice problems, I'll pretty much use the conclusions that we have instead of going back to saying, remember, that's what this means. So if we have this angle X, let's say I take this angle and move it over here. This is the same angle, keep that in mind. If I make it an inscribed angle, as in the vertex touches the circle instead, you get this intercepted arc. I'll draw it red. Now this intercepted arc is not B, by the way. B is this entire green part right here. Okay, so all of that is B. And the question is, well, what's the red? Because if I have this angle here, X, okay, if this is angle X, this intercepted arc, that red, should be half the measure, or should be twice the measure of X. X should be half the measure of the intercepted arc. So the question is, when I start to pull this back, notice how this red here is not my intercepted arc anymore for this particular thing that I pull back. I keep going and it merges with the green. And the question is, how long is this orange part right here, the part that's not red? How long is that plus that? The answer is this entire bit is the same as this measure right here, A. That didn't really work. A right here is the exact same as this orange right here and here. So when I pull this angle back, the amount of intercepted arc that I gain, excuse me, the amount of intercepted arc that I gain in the green that's not red is the same as this measure here. So this entire B is that part plus A. Or better yet, this part is B minus A. So this intercepted arc here, this red, is B minus A. So if that's B minus A, X equals half the measure of that. The reason is because X is an inscribed angle, and an inscribed angle is half the measure of its intercepted arc. This red right here, just the red, is B, the green, minus A, minus that part right there. So X would be half of that. Okay, next part that I want to look at is putting A and B together. A is this minor arc, and B is this major arc. Together, they make one circle right here. So the entire measure of A plus B is equal to 360 degrees. A plus B equals 360. That might help you in your own way, but it's going to help me solve the next thing here. Third thing I want to say is, let's say I draw a central angle. Let's say I draw a center. Now I create a central angle right here. My intercepted arc right here is the measure of A. Okay. A, as an intercepted arc of a central angle, has the same measure of its central angle. So if this is A right here, then the central angle is also A. I know I wrote a different lowercase a, but both of these are A degrees. Central angle, if this is 150 degrees, this is 150 degrees. So why does that matter? Well, what I just formed here was one quadrilateral right here, all in blue. This is all one quadrilateral. These are tangent lines right here and here, mixing with a radius. Remember, this is the center. The radius intersects with the tangent line at 90 degrees. So if these are both 90, in a quadrilateral, I'm looking at this angle plus this angle plus this angle plus this angle equaling 360 degrees. The sum of the angles in a quadrilateral adds up to 360. If that's true, then x plus a plus 90 equals 360. And if you keep working this out, remember the shortcut here. These will always be 90 degrees as long as these are tangent lines. As long as they're tangent lines intersecting with radii. So x plus a equals 90 plus 90 is 180. Subtract 180 from 360, you get 180 degrees. So x plus a is 180. This is kind of important to know in terms of if I need to solve for a, what this intercepted arc is, and I only know these two right here, you can say that a equals 180 minus x. Okay? Measure of this arc A, or the central angle A, is the same as taking 180 degrees and subtracting x from it, because these two angles add up to 180 together. Okay? Now I can do the same thing. If I use this rule right here, A plus B equals 360, I could start talking about what B could equal. If A plus B equals 360, and A is also 180 minus x, let's substitute 180 minus x in for A. We'll get 180 minus x plus b equals 360. Let's add x to both sides here. 180 plus b equals 360 plus x. And now subtract 180 from both sides. B equals 180 plus x. Okay, so b over here equals 180 plus x. So here are four different conclusions I can make. This one, I don't know if I necessarily need that one. You could include it just as we did. But here are our four rules here. Four that you would definitely want to know based on this diagram. So this is a good worksheet to keep with you. Something that you'll always have with you by your side. And you can look at these rules and say this is what they mean. More importantly, it's how you look at them, what you understand with them, why they work. Because you might not be able to use these to keep them in memory, and whatever for a test, you might have to memorize them. And I wouldn't ask you to memorize them. Instead, I'd say, hey, take what you know about these things, apply the rules as you can. Okay, so those are four conclusions that we can draw based on this right here, based on the information I gave you. Okay, the next sections I want to talk about are secant lines. Now, we haven't talked about these yet. I don't know if you've heard the word before. A secant line for a circle is if we have this point right here. Remember what a tangent line is. If I extend a line out and it touches the circle at just one point. That's a tangent line. Any other line that goes out here doesn't touch any points is nothing. A secant line is a line that touches through the circle at 2 points. So instead of a tangent here, here's an example of a secant line. And secant line, secant line, secant line, etc. All of these are secant lines, including this one down here, because it crosses through the circle at 2 points right here. So these are known as secants. Tangent, 1 point, secant, 2 points. Okay? Within a secant, within those 2 points, you formed a chord right there, like this length here. It's unknown. We can even call it y. So we're going to look at that on the next page, those unknown lengths and what we can do with them. Okay. Now, secant line, however, is not much different from, well, there are differences than a tangent line, but in terms of angles, they still have the same kind of properties applied to them. Let's say I take this angle here, x. I group it up. Let's see. Let's take this blue here. Okay, this x angle right here. I group this up here, and I try to move it in as an inscribed angle, like this again. Okay? This is no different from what we did before. We want to find out what the measure of this intercepted arc is. Remember, it's not B. B represents this. Let's see. B, once again, represents the green. If that's red, this is B, this major arc right here. I want to find out what the red is. And the red is, if I pull this x back out to where it was, watch how much, and again, I'm pointing my finger on the screen. That doesn't really work. But watch right here and watch right here when you get this black starting to show up as I pull this out. To pull this out, its intercepted arc is not just the red, but it's also that black. And that black, as I pull out, is the same exact length. This part plus this part is the same length as this A together. So if I want to find out what the measure of this intercepted arc is right here in the red, again, it's taking all of B, subtracting this part and this part. This part is the same length as A right here. Subtracting A, and then I get that intercepted arc right there. So the intercepted arc is B minus A. Okay? The entire thing, I'm sorry, not the entire thing. The inscribed angle, however, is half the measure of the intercepted arc. So half the measure of this intercepted arc, x, would be 1/2 of b minus a. Okay? Just like we did up top. X equals 1/2 b minus a. It's no different. This thing outside here is still the major arc minus the minor arc. That would be its intercepted arc. Take half the intercepted arc to get the inscribed angle. Okay? And once again, one more time, no different here as I move over. If this is x, I'm going to do this one very quickly. I make it an inscribed angle. Group it up. Let's make this inscribed angle over here and say, what's this intercepted arc? Whatever this thing is, we'll take half the measure to get this angle. Because remember, this angle doesn't change. This thing right here is the same as this thing right here. As far as an angle goes, this angle is no different. So look at this intercepted arc, take half of it, and you'll get x. So x is half of b minus a. If you can't really see it and stuff, then I understand. Here, what I'll do is I'll lay it over here. Pretend like this is that intercepted arc right here. Can you kind of see that these two are the same? Hopefully you can get an understanding and say these two are the same thing. And if this whole thing is b, let's take away this part and get what's left. And what's left here will just be that red portion right there. Okay? This red portion is twice the amount of this right here. Remember, this is x down in here. X equals 1/2 this measure. This red guy right here is b minus a. So once again, for both cases 1 and 2, angle x is still half the measure of your major arc b minus your minor arc a. Okay, so this measure outside of here is still that. I'll go ahead and erase this. And I'll move on. I'm actually going to draw one more thing down here, just a little footnote for the next thing you're going to see. Even though it's not in your practice problems, per se, as far as finding angles, it's important to know. Looking at inscribed angles one more time. Let me draw one right here. I'll get x and x, or I'll get x right here. Okay, here's an example of an inscribed angle with these two endpoints. Let's say these are v and w. Remember, all inscribed angles have the same measure. So if I draw that inscribed angle, they have the same measure. This inscribed angle has the same measure as the other one. Let me draw them outward. Okay. So keep in mind, this guy and this guy have the same angle measure. So we've done this before. I kept drawing these out. I'll do one more, like this. Okay. All of these guys are congruent. Another one that's congruent, by the way, is a line that's tangent to one of the endpoints, and its vertex is also on the endpoint. So look at this bigger green one that I'll do right here. If I draw a tangent line out from V, so let's pretend like this line is like tangent to V, as in it crosses here at just one point. And I create that as a vertex, and I draw the other endpoint through W. This angle, I don't know if it's called an inscribed angle still, but by rule it still has the same measurements. This angle is congruent to all these ones as well because its vertex lies. Okay, yeah, so let's call it an inscribed angle. It's an inscribed angle because its vertex lies on the circle and it hits the same two endpoints as all the other ones. So if you look at this blue one right here, vertex is on the circle, endpoints are V and W. This light blue one, vertex right here, vertex is on the circle, endpoints are V and W. This darker teal one, vertex is on the circle, endpoints are V and W. Now this green one, vertex is on the circle, and its endpoints are still V and W. The fact that it doesn't have an endpoint way out here is irrelevant because this line is tangent. It only hits this at one point right there. Okay? It's tangent, but this still has the same angle measure as all these guys. It looks a little jarring, a little bit confusing there. Let me erase some of these. I'll erase these ones and just keep that dark blue one. These both are congruent. So if this one is 30 degrees, this one is 30 degrees. Now the question is here, what is its intercepted arc? And the answer is its intercepted arc is the same as it ever was. Just like the other one, its intercepted arc is right here. So if this guy right here is 60 degrees, this blue is still half the measure, which is 30, as we know. But this green one also is half the measure right here. This is also 30 degrees because it's an inscribed angle for this intercepted arc. Something that's visually difficult to see, and when you stumble upon one of those problems, it's going to be difficult to solve. But I need to use this example to let you know that that's exactly what they are, and that it's still an inscribed angle. So that would be let's call it a tangent inscribed angle, just so you have a footnote of another kind. And the thing I want to put here, if these are V and W, let's call this X. Let's call this point out here Y. So I want to say that angle YVW, this guy right here, is congruent to angle VXW. Okay? So these are congruent because they're both inscribed angles. They both have the same endpoints V. Well, sort of. V and W, V and W. Remember, this isn't an endpoint. This is a point out in space. I mean endpoint on a circle. Okay, let me just do examples with those first. I'll go ahead and go to CW number 8 as I do it. That way it's fresh in memory. And then we'll do the next one involving lengths and talk about those in a bit. Okay, let's get to work here. Using what I know, using our conclusions and our rules, we can solve for different things. So if we have secant lines or tangent lines, what does x equal? What does y equal based on major and minor arcs, etc.? Okay, so once again, I'm going to apply the rules. I'll just insert the correct formula as I go along, and without too much description of whatever. But if you still have trouble, I do want to clear those up with you as well. Okay, we have an example of two secant lines here, two secant segments at least. Here they form an angle x right here. Remember, x would be the inscribed angle out here that forms the measure that's 150 minus 70. So the intercepted arc here would be 150 minus 70 degrees if this was x, which is 80 degrees. So x equals 1/2 of 150 minus 70. X equals 1/2 of 80. So x equals 40 degrees. By the way, all the answers are on the bottom. I want to double check with myself and make sure they're correct as I go. Or I want you to do that as you work along with this. Okay? Here's another one. I assume these are tangent lines right here. It keeps going out, touches the circle at one point. Nevertheless, I got a major arc and a minor arc, and I have an angle where if I moved it outward, it would be an inscribed angle that would be 300 minus 60 degrees. So x, the angle measures 1/2 of that intercepted arc. X equals 1/2 of 300 minus 60. X equals 1/2 of 240. So x equals 120 degrees. Okay, double check that with the bottom for yourself. Make sure I'm not incorrect there. Moving on here. X, once again, two secant segments right here. If I put x inside here, inscribed angle, that would be 60 minus 20. So x, the angle measures 1/2 of that intercepted arc, 60 minus 20. X is 1/2 of 40. So x equals 20 degrees. Okay. Looks like I applied the same rule each time going back. I looked at this one each time that I did this kind of problem with tangent lines or secant lines. We didn't see a secant with tangent line, but we sure will as we keep moving on. Any questions on that? Okay, let's keep going. Okay, here we go. Here's an example. And this one's a little bit different because now x is not the angle measure. X is the minor arc. Now remember, if I take 31 degrees and I move it out into here, I can create an inscribed angle of 31 that would be half the measure of its intercepted arc. And its intercepted arc would be 168 minus x. Major arc minus well, this isn't necessarily a major arc, but the bigger one. Okay, so 31 degrees equals 1/2 the measure of its intercepted arc, 168 minus x. Okay? You can either distribute the 1/2 into here. I'd rather just multiply both sides by 2. If I multiply this side by 2 and this side by 2, then I'll get 62 equals, now 2 times 1/2 cancels out both of these guys. So you're just left with 168 minus x. Add x to both sides. X equals, subtract 62 to both sides. 168 minus 62 is 106. So we got that there for x. Let's double check that. Yep, we got it. Now there's another one here, y, and it's another arc. It goes from here to here, and we're trying to figure out what it is. Well, x equals 106 degrees. And together, this entire circle should equal 360 degrees. So 106 plus 168 plus y equals 360. Okay, this is an example of saying this one right here. A plus B equals 360 degrees. Even though here I only have 2 arcs, and the other one I have 3, I can connect 2 of them. Let's connect both of the, or are we? Let's connect both of these guys right here, 168 and 106. 168 plus 106 is 274. So 274 plus y equals 360. So again, if you take a look, let's pretend like this was B, okay, and this was A. A plus B still equals 360. This B is 274, the A is y. Subtract 274 from 360, and you get y equals, I think that's 86. It's 86 or 96. I can't do the math in my head. Y equals 86 degrees. Okay, so y equals 86. Yeah, that's solving those. All right, looking right here. Oh, and by the way, I didn't see this rule right here, or I didn't use this rule yet. I didn't look at these. These are tangent lines right here, intersecting tangents. These both will be congruent. We proved that the other day, talking about similar congruent triangles and whatnot, using the center and doing all that stuff. Okay, so those two are congruent. So when we solve for this down here that I noticed, k, because we're about to talk about length in a second, these are both tangent lines, so k and 5 will be congruent, so k equals 5. I'm assuming 5 units. They don't show centimeters or inches or anything. Okay, m represents the angle, n represents this guy right here. Now, if you remember, now this is something that I guess I'll bring up again, because this is something that you might not remember as you go. You're like, well, I don't know what to do here. You know that n plus 218 equals 360. So let's go and start with this. N plus 218 is 360. This arc plus this arc. Subtract 218, you get n equals 142. All right. Okay, n is 142 degrees. Right there. Okay, so if n is 142, that's not only the measure of this arc right here. The arc and central angle are both congruent. So this is also 142. If you remember, when you draw radii intersecting with tangent lines, these are 90-degree angles. So we always said that these two, if these are 90, these add up to 180. These also have to add up to 180. So m plus 142 equals 180. Or better yet, as we put, m was our x over here. Here's x. 142 is our a. A, like 142, equals 180 minus x. Okay? We had that, but we have to set it up the other way to solve for this as we go. Let's just go ahead and subtract 142. We get m equals 38 degrees. Right there. Again, I was using the rule, but I wanted to talk about that one more time because, it's something that you don't see, right? They don't give you a center. I want you to be able to draw that for yourself if you're totally lost in those things. And again, you might not memorize those rules and formulas. Okay, so that's practice with angle measures. I'm going to go ahead and now talk about lengths. And in doing so, I have to use 2-column proofs and such to start talking about these and making sure that some of them make sense. There's a lot of practice into this. It needs to come into fruition for you guys. 2-column proofs need to, work. I need you to get them. Let's go and work with them. Lengths. Secants and tangents. We haven't talked about lengths too much except for this one over here. Tangent lines form congruent angles, or form congruent segments right here. And we did that using triangles. We have to do the same thing here again, figuring out what all this stuff means. How do you solve for B and C and A and such using things? Here's what I'm going to do. I'm going to make 2 triangles. And let's give them different colors. I'll make one green. Whoops. I'll make one green right here. It'll connect these guys. Make no mistake, don't assume this is a right angle because it's not always going to happen to be a right angle, even if that actually was. And then I'm going to make another one here blue, and I can't really overlap it fully. I want to make sure you can see one and the other. Okay. I have 2 triangles right here. And you know what? I probably need to assign letters to this kind of thing. That way I can prove triangles similar. Obviously, these triangles aren't congruent. I want to prove that these 2 triangles here are similar. So let's go ahead and let's call these W, X, Y, and Z. And I want to prove that triangle WXZ is similar to triangle, I think it would be YWZ. What I'm basically going to do is show two sets of angles that are congruent, then use angle-angle theorem to make my statement that I want to make. So let's do statements and reasons, because the whole thing is about, I need to talk about what segments are proportional. Remember, we did this with chords. We proved two triangles similar. We found out what could work with intersecting chords and what parts intersect, all that stuff. Okay, first statement I'm going to make is you can see in both triangles here, they share this angle, angle Z. So angle Z right here is congruent to angle Z by the reflexive property. We've used reflexive property more often with sides like these two guys right here, this green and blue. Sides being congruent by reflexive property. Because we would say that if we're proving triangles congruent, they both share a side, such as that one, and those sides are exactly the same thing, therefore they're congruent. Same thing here, shared angle in both triangles, so angle Z is congruent to itself by the reflexive property. Okay, moving on with that one. Here's another set that's congruent, and here's why I had to talk about these tangent things right here. Remember, we said these are both inscribed angles for the same two endpoints. So I want you to focus on the fact that there are two endpoints right here for this angle and this angle. Look at that for a sec, and now we're going to look back here. Look at this angle X and this angle right here, YWZ. They both have endpoints W and Y. Let me draw those in red. These endpoints in red are W and Y. This inscribed angle right here, X, uses W and Y. This inscribed angle right here, remember the vertex is on the circle, and its endpoints share the same endpoints as these other guys. These two guys are congruent for that very reason. If this was 45, this is 45. Okay, so I'm going to make one more statement here. Let's erase those because I want to see these triangles in full. Make one more statement here and say that angle, I'll call it WXY, is congruent to angle YWZ because they're both inscribed angles with the same endpoints. I'm just going to put inscribed angles. And finally, now that I have two sets of angles congruent in both my triangles, in triangle YWZ, I have this unknown so far. Remember, we didn't know this was a right angle. We're not going to say it is. No idea. YWZ, it goes from no known angle to W to Z. And then WXZ, no known angle right here, all of W, to angle 2 to angle 1. Right, so this is none, 2, 1, none, 2, 1. So I'll say triangle WXZ is similar to triangle YWZ by angle-angle similarity. Okay. So what's the point of doing angle-angle similarity? Why do we end up doing that? Why do we show it? Well, let me see if I can start grouping all these things and make sense out of that as I go. Let's group all the blue ones together. And one more angle measure right there. Group it and clone it. Copy and paste. I'm going to stick it right there. Then I'm going to take the green one right here and do the same exact thing. Oh wait, I have to ungroup first. Hang on a second. Let's try and get this again. Ungroup. I don't know how to ungroup. Control R. Okay, let's take the green ones right here. Try and group all these together. Copy and paste. Oh, well, I got the blue segment. Okay, no worries. Pretend like it's green. In fact, I'll draw it green. Again. It's green again. Haha, I gotcha. Group that together. Okay, here's what I'm going to do. I'm going to relate these things so they're the exact same here. Let's rotate this over, and it's flipped over. So let's flip it. Flip it good. In fact, I got to take, here, one more time. I'm sorry. I got to take these angles, make them the same. This was W, Z, and Y, and it here was Z and X and W. Here's how they're similar. The important thing here is I need you to see the corresponding parts, right? Because it's hard to see what actually matches up here. I need to rotate this, and you'll see that this angle and this angle aren't matching up. They're on opposite sides. So I need to flip this guy. Flip it left and right and see what we got. Okay, now I can start rotating this. All right, now we're looking at how these triangles are similar, right? Same angles, right? Congruent angles here, here, and the unknown one here, but they have different side ratios. Okay, now I have this W, Y, Z that's all flipped and messed up. Okay, and now I want to rewrite those as W, Y, Z, up, right side up, W, Y, Z. So you can see what things relate to one another. X and W in these two triangles relate, are congruent here. Oh, by the way, this blue. Okay, let's do this. X from X to Z is A plus B. That length right there, A plus B. This length right here is C. Okay? Now over here in the green, from W to Y, I don't know what I have. From Y to Z, I have A. From W to Z, I have C. Okay? Now let's create side ratios. Okay, here was the whole point of all this. I have to create side ratios here. A to B, A plus B is to C. This is to this. As this is to this. As C is to A. Okay, cross multiply. What do you get here? If I multiply A with A plus B, I'll get A times A plus B equals C squared. Okay, so that's my conclusion. I did a lot of work to get there, but my conclusion is this, and I'm going to erase this top stuff, all those blue markings and stuff, and I'll undo it if I need to. Look at this. A is this part right here times A plus B. That is the outside segment times the whole line equals the outside segment times the whole line. Even though the outside segment is the whole line. C times C is outside segment times whole line. So I'll write that in. Outside times whole line, that's a times by the way, equals outside times whole line. Okay? And moving on down, excuse me, and moving on down, we're going to have the same thing here. It looks like I'm running out of time to really prove this, but I'm going to go super quickly with it. No statements in reason, or no two-column proof to write. But let's look at this green triangle here, and this blue triangle here, if you can still see the green there. Okay. Whoops. Okay, what we're going to end up having here are reflexive property. Here's a shared angle in both of these guys. If this was W, X, Y, Z, oh, whoops, I forgot a letter. Let's call it V. Angle Y is congruent in both triangles here by reflexive property, shared angle. Okay, now what I have here, I'm going to draw in different colors one more time. I'll use red. Whoops. I'll use red there, and let's go good old purple. Purple there. Red and purple are both inscribed angles. If you can just see purple with endpoints V and W, and red with endpoints V and W, those guys are congruent. So if purple is congruent with red, and these are supplementary lines here and here, then this angle in green is congruent with this angle in blue. Because again, inscribed angles there and there show supplementary angles will also be congruent. So angle X is, the angle X in blue is congruent to the angle Z in green. So by angle, you say that triangle WYZ, the green one, is similar to triangle VX, let's say WYZ, VYX in the other one. So if you have triangle WYZ with side length A plus B over there, and this is C, and then you have another triangle here, the blue one, that's VYZ. From V to Y, I have C plus D, and then here I have A in blue. We have another proportion to set up. We got A plus B is to C plus D from here to here, as C is to A. Excuse me. And if that's true, then that means A Cross multiply. A times A plus B equals C times C plus D. Okay, if I erase all this right here, you'll see that this is still the outside A times the whole segment A plus B equals the outside C times the whole segment C plus D. So there's something that's true in both these guys. Doesn't matter if it's tangent or secant line, it's outside times whole thing equals outside times whole thing for both. Okay, got like 5 more minutes to do some examples here, so let's go through them. So, for example, setting up this thing, outside times whole thing, 4 times 4 plus x equals, on this side, outside times whole thing, 8 times 8, which is 8 squared. 16 plus 4x, and sorry, I'm going to save you the math here. I'm just going to work through it quickly here. X equals 12. So this length right here is 12 because of that proportion that's set up. Remember, these are all set up from similar triangles. Even though you can't see them, they all set up from similar triangles. Outside plus whole thing equals times whole thing equals outside times whole thing. So I'm going to keep saying that as I go. Equals 3 plus 6 is 9. 3 times 9 is 27. So x is the square root of 27. That's the square root of 9 times the square root of 3. Square root of 9 is 3, and square root of 3 is square root of 3. So x is 3 root 3. I think on the bottom they showed 5.2 or something like that. Okay, outside times whole thing equals outside times whole thing. Again, I'll just keep saying that. Let's make sure that we get that principle here. 4 plus 6 is 10. 10 times 4 is 40. So x squared plus 3x minus 40 equals 0. This is an algebra trick, remembering how to factor this, figuring out what two products multiply to negative 40 and add to 3. That's positive 8 and negative 5. And you solve, you get x equals negative 8, comma 5. So either of these solutions work. Problem is, x is a length here, and length can't be negative. So x cannot be negative 8. Negative 8 does not work here. The only thing x can equal here is 5. I'm sorry I'm rushing through these examples. Obviously, I've run out of significantly amount of time here. I had a malfunction earlier. Okay, outside times whole thing equals outside times whole thing. 5 plus 7 is 12. 5 times 12 is 60. So 60 equals 36 plus 6x. Subtract 36. You get 6x equals 24. And x equals 4. Okay. And finally, last one here. Let's do the lengths first because we're practicing it. Outside. Whoops. Oh, right. Outside times whole thing. 6 times 6. That's 6 squared. Equals outside times whole thing. 36 equals 16 plus 4x. 4 times 4. 4 times x. Subtract 16. You get 4x equals 20. So x equals 5. Okay, they're about to come in. X equals 5. Final ones. Angle right here is half of 108 minus 42. So y equals 1/2 of 66 times 1/2. Y equals 33. Sorry, you guys are piling in. And yeah, so just keep in mind, x was this length right here, wasn't that arc. Okay, so like I said, this video would help with everything. If you have everything filled out here in this one, it should really set you up for everything you kind of need to know.